Hi and welcome to the class of real analysis, and today we will continue our discussion on the sequences. And in order to start the class, we will start with the theorem, an important result, that is the uniqueness of limit. So a sequence cannot converge to more than one real number. So what does it mean when we say that it does not converge to more than one real number? So that is, it will converge to a single real number that we call as unique. So the limit of a sequence is unique. Uh, and To start with the proof, let us consider a sequence. We call it xn. We are already familiar with this notation, that is xn in the bracket. It represents a sequence with a limit. So the limit of the sequence is and when the sequence tends to when n tends to infinity for the sequence, the limit converges to L. And then we again say that limit n tends to infinity xn equals to m. So we take two real numbers, m and L, as the limits of the sequence, and we will show that actually this L and M are equal in order to prove that the limit is unique. Since the sequence is converging to the limit, then therefore the sequence is convergent. So by the definition of the convergence of a sequence, we have that there exists some n1 belongs to the natural numbers such that n is greater than n1, implies that xn minus L in the mod is less than epsilon. Okay, so it's by the definition of the limit, it's by, we can say, by definition of convergence. So we said that the sequence is convergent and it converges to a limit L and M. So again, there exists n1 belongs to naturals such that n greater than n1 implies xn minus L is less than epsilon. And since we also say that xn is converging to m as well, so there exists again some n2 as well, which belongs to the natural, such that n is greater than or equals to n2 implies that the mod of xn minus m is less than epsilon. Okay. Now, when we say that the sequence is converging to two limits, so we have n2 and n1 belongs to the natural such that n is greater than both of n1 and n2, and other for the convergence of the sequence, then we can take n naught as the maximum of n1 and n2, because if n is greater than n1 and or equals to n is greater than or equals to n1, and n is greater than or equals to n naught, n2, then the maximum of n1 and n naught, so we are taking n naught as maximum of these both numbers, maximum of n1 and n2, because if say n1 is the maximum between n1 and n2 and n is greater than n1, then it's uh, obviously greater than n2 as well, because the maximum is n1, and if n2 is the maximum, then obviously this n1, if n is greater than n2, and then so it's ultimately will be greater than n1. So we are saying that n naught is the maximum of n1 and n2. Therefore, we can say that this instead of xn minus L, now we are saying that xn naught minus L. Why we can say that? Because we know that we are saying in the definition that when n is greater than equals to n naught, so instead of this xn here, I can replace n naught because of this equality here. So since it's greater than or equals to here, therefore I am replacing this n with n naught. So xn naught minus L is less than epsilon. then similarly xn naught minus m is less than epsilon, then xn naught minus L plus xn naught minus m in the mod is less than epsilon plus epsilon. We can do that in the mod. So the right hand side will be 2 epsilon, and we can say that 2 epsilon equals to epsilon prime. So its epsilons is a small number, since so when we multiply it by 2, it doesn't affect that much, because this is a very small number. So when multiplied by 2 is still a very small number. Now by triangular inequality, we know that mod of x plus y is less than or equals to mod of x plus mod of y. So this is like mod of x plus mod of y, and it's less than 2 epsilon, and this thing is less than this thing. So we can replace this thing instead of this thing, because this is less than this thing. Okay, so we can replace here, because here is the less than sign. So we can write L minus x naught plus x naught minus m in the mod is less than epsilon prime. So we replace this with this thing here in the mod, because by using the triangular inequality. So we have and then this is L minus x naught in the mod, so it's in the mod since, so we can write x and naught minus L as well, so it doesn't matter. And we can write L minus x naught, so it's the same because it's inside the mod, right? So it's L minus x naught plus x naught minus m, and x naught cancels, so we have L minus m in the mod is less than epsilon prime. Now we are using a theorem here that is called the forcing principle, which says that if for all epsilon greater than 0, mod of a minus b is less than equals to epsilon, then we can say that a equals to b. So by using this principle, we can say that here, because we have L minus m is less than epsilon prime, which is again epsilon, it's a small number, so we can say that L equals to m, and the proof is done, because we need to prove this thing that L is equals to m, since the limit is unique. It is proved that the limit is unique, because we assume that the sequence is converging onto two different limits, but again we come to the conclusion that both are equal, which means that that is unique. Now there is a definition that a sequence xn is bounded if the set xn such that n belongs to n is a bounded set. There are two equivalent ways of saying xn is bounded. So a sequence, it's about the bounded sequences. So we call the sequence bounded if there exist a comma b, two numbers belongs to the reals such that for all n belongs to the naturals, this xn, this sequence is bounded between these two numbers a and b. And also we can say in this manner that there exists some number m greater than 0 such that for all n belongs to n, the mod of xn is less than equals m, which again implies that xn is between negative and positive m, because it's in the mod, right? So now we have one more theorem here, that every convergent sequence is bounded. Okay, so if a sequence is convergent, then it's bounded. So we are going to prove this theorem. So let xn be the convergent sequence. I'll say that xn is converging to L. This is the notion for convergence. Then taking an epsilon, arbitrary epsilon, taking epsilon as a constant, because a small number, you can say it's a constant. So if we are calling it C, then by definition of convergence of sequence, there exists some n naught belongs to the natural such that n will be greater than equals to n naught, implies that xn minus L will be less than the constant C. Then we can remove the mod here, and we can write in this way as well. So we have and then adding L on all sides, we have L minus C less than xn less than L plus C, and we consider that let A be a number that is the minimum of this sequence, that is still L minus C. So L minus C is a number of the sequence. It's a member of the sequence. It comes after some xn naught, and again taking B as the maximum of the sequence, still L plus C. Since L plus C is in the sequence, then for all n belongs to n, we can say that this xn is bounded between A and B, because for this L minus C, we can replace A because we are saying that this is minimum than all these numbers. So if it's minimum than all these numbers, so this is a bound for xn, because L minus C is a bound for xn. So if A is less than L minus C, or we are saying that minimum of, sorry, not less than, A is basically minimum of all these terms. So the minimum of all the term is A, and the maximum of all these terms is B, then my xn is bounded between A and B. So therefore, xn is bounded. So whenever we have a convergent sequence, then it's understood that it's bounded, and this theorem proves that thing. Now I'll talk about the algebra of limits. This is very important topic. Okay, so the limit n tends to infinity, some constant c times xn. So we can take out the constant and we can apply the limit onto the sequence directly. So it's we can say that it is interchangeable. The limit and constants are interchangeable. We can just take the constant outside. And again, then for simple addition of two sequences, a limit n tends to infinity xn plus y, and then the limit operator can be applied to the individual sequences. Similarly, for the subtraction, we can do same thing. And for multiplication, again, we can do the same thing, that we can separate both and apply the limits and take the multiplication sign in between, applying limits individually on xn and yn. We can do that. That is the algebra of limits. And for this thing in the division as well, we can write in this manner: limit n tends to infinity 1 over yn. We can apply the limit in the denominator with yn, since 1 is constant, so nothing to do with the limit. And again, for this ratio x and y, and we can write separately like this. And we will take some problems for better understanding. Then again, the square root and the limit is also interchangeable. Okay, so we can take some problems for better understanding. For instance, let's say that suppose the limit n tends to infinity xn equals 5, limit n tends to infinity yn equals to -3. Find each of the following limits. So we'll use the algebra of limits. Now we have n tends to infinity 2xn minus 3yn, where xn equals 5, yn equals -3. Now we can apply the limit individually by the limit algebra of limit theorems. So we applied the limits individually, then we can take the constants outside. We have the first theorem and first theorem of algebra of limits. So 2 outside and limit will be applied to this, 3 outside, limit will be applied to this, and these values are already given in the question. Apply the values and we'll get the answer, that is 19. Now let us consider this example again. Now we know that the limit is interchangeable with the square roots and the powers, so we can write this limit n tends to infinity xn squared as limit n tends to infinity xn whole squared. Okay, so the powers and the limits are interchangeable, so we can write in this way. And here first we applied the theorem of the ratios of the sequences, that we can apply the limits to the numerators and denominators individually. Therefore, we did here in this step, and then we applied the limits inside, and we apply inside and then take the square like this. So it's fine, we do that, we can do that. It's these examples are for visualization, that how we can do these examples. So here we did that, we take out 2, we can do it. Remove the constant outside, from inside the limit, and in the denominator we can see that we have applied the limit individually on xn and yn here and here. So we can just plug in the values simply. For xn we have 5, so it will be 5 squared, because limit xn tends to infinity, xn is given as 5. This is given as -3. Apply the limits and get the answer, that is -7/60. And for the mod as well, we can do the same thing. We can take this limit inside the mod to solve the limits, and then at the end we can apply the mod. So we will get the correct answer, that is 1/8. Like, you can follow these steps. We applied the limit inside the mod, then we uh, put the values, and then at the end results we just remove the mod, so it makes positive 1/8. Then we have limit n tends to infinity, 1 plus square root of xn over square root of 1 minus yn. Again, using the property of algebra of limits, we can take this limit n tends to infinity inside the root, and this limit n tends to infinity 1, so it's a constant, nothing to do with the limit, it will remain constant, that is 1. And this limit goes inside the root, and limit n tends to infinity xn is known to us, so this will be square root of 5, we can see here. And here also in the denominator, the limit goes inside and applied individually to the elements, that is 1 and yn. And similarly, we plug the values and get the answer that is required. Now find the limit of each of the following by using algebraic properties of the limit. Okay, so we can find, similarly, we can do similar things. Now here we have this whole squared. So first of all, we can take n common outside, so it will be n squared because it's whole squared. So this will be n squared into 10 minus 11 over n squared into 7 over 7 over n minus 2. Then n square cancels, then limit comes inside and operates on the elements individually, and then taking a square we get the answer, that is 25. You can look at the steps, you can do practice in your copies, so it's important. And similarly here we did the same thing. This is the question, limit goes inside the root, operates, and the limit is applied individually. We get the result, that is 0. Now for this question, we have proof that each of the following sequence diverges. So if the sequence diverges, we can show that it's unbounded, because we know that every convergent sequence is bounded. So if it's diverges, so it means that it's unbounded. So it's enough to show that this sequence is unbounded, and we can show that easily if we can show that a sequence that is smaller than this sequence and diverges, so this sequence also diverges. So similarly we did here, that is 2n plus 3 over square root of n. We know that this is greater than 2n over square root of n, because here is 2n plus 3, so obviously it's greater than this element here. And we can manipulate this n over square root of n, as we can write n as square root of n times square root of n divided by this, so we'll get square root of n. So we have 2 square root of n, and we can see that this sequence here is of course divergent, right? Because it's increasing and increasing and increasing without bound. So it's unbounded. There is no bound, so it's diverges, which implies that this sequence is divergent.